Okay, so last piece of all the position, velocity, and acceleration for now. I want to show you what the graphs are going to look like. So I want to look at a couple of different things. Let's say I have a couple of different cases. The first one we're going to look at is a constant or an unchanging, right? A constant or unchanging x, an unchanging position. So what does that look like on these graphs? Okay, if my x doesn't change, if I start at some value, let's say 1 meter, okay, here I am at 1 meter, I'm not moving. So what does my position look like? Not very interesting, right? After 1 second, after 1 second, I'll be at 1 meter, okay? After 2 seconds, I'll still be at 1 meter, and after 3 seconds, I'll still be at 1 meter. I'm not changing, just standing still, right? So I have a flat line. If I have a constant x, wherever I start, if this is 1 meter, or 10 meters, or 100 meters, wherever my starting position is, that's where I stay. Could it be at 0? Absolutely. It's just going to be a little bit hard to see on this graph, but I could start out at 0 meters and just stay there the whole time, okay? So what does my velocity versus time graph look like for that? Well, am I moving? No, I am not, okay? So after 1 second, 2 seconds, and 3 seconds, I start out with no velocity. Okay, I'm not moving, not changing my position over time. After 1 second, I still haven't changed my position over time, so I'm still at 0. After 2 seconds, I'm still at 0. 3 seconds, still at 0. I've got a very uninteresting velocity versus time graph. Well, again, I'm not moving, so that makes sense. I have no velocity. I'm not moving at all. I have a constant position, so I have no velocity. All right? What about my acceleration? Well, again, I'm not moving. I have no velocity to begin with, but I'm also not adding any velocity to that over time. I'm not starting staying still and then speeding up as I go, right? I'm not accelerating forwards. I'm standing still. So again, my acceleration was 0, stays 0, continues through 0 the whole way. I got a flat line for my acceleration. It's a very interesting set of graphs, isn't it? Okay, so for constant position, okay, unchanging position, you're going to have a flat line here, and you're basically just going to have a flat line at 0 for both velocity and acceleration. Very uninteresting. Okay, so let's take the next example where I have, well, let's put a couple more increments on here. Let's say 1 meter, 2 meters. Let's say now instead of a constant x, we've checked that one off the list. Okay, that one's gone, all right? So now let's say we have a constant velocity. All right, constant velocity. Well, what our velocity is matters, doesn't it? So let's say that our velocity is actually 1 meter per second. All right? And let's also put another thing in here because it also matters where you start. Our initial position is going to be 0 meters. Okay? So where do we start? Well, we start at 0. Okay, that's my initial position. I'm starting here. But I have a speed. I'm walking at a constant rate. I'm going at the same speed the whole time, so my position is changing at a regular rate. My rise over run is going to be consistent. I'm going to have a consistent slope here. Because after 1 second, right, every second that goes by, velocity times time gets me my final position. Okay? So after 1 second, 1 times 1, right, velocity is 1. After 1 second, 1 meters per second, after 1 second gets me 1 meter. So after that, 1 times 1, I get 1. All right? So after 1 second goes by, I end up at 1 meter. There I am. Okay? So if I'm going like this, after 1 second, here I am. Maybe 2 seconds, I'd be off the screen at that point, right? What about 2 seconds on here? Okay, so if I have a constant velocity of 1 meter per second, and I'm going for 2 seconds, 1 times 2 gets me to 2 meters. See? Very regular increase, right? If I'm going at a constant rate after 1, 2, I've covered the same amount of distance between each second. So now I'm at 1. I've covered 1 more, right? Or really, if I would just want to know overall, I'm going 1 meter per second for 2 seconds. I've gone 2 meters in total. So after 2 seconds, I've gone 2 meters. Okay, so let's connect the dots up here. This should be consistent if I drew this consistently. Should have a nice, consistent thing here. and 3 meters, 3 seconds in, 1 meter per second for 3 seconds. 1 times 3 will give me my final position, which will be 3 meters after 3 seconds, right? Or 1 more meter after 1 more second. My rise over my run, my slope will remain consistent the whole way. So, what I want you to see here, on a position versus time graph, a velocity, a constant velocity, an unchanging velocity on a position versus time graph looks like a straight line. As long as you have a consistent slope, you have a consistent velocity. Okay? What does that same consistent velocity look like on a velocity versus time graph? Well, I started out with a velocity of 1 meter per second. Okay? So here I am over on my velocity axis now for a totally different graph. I have 1 meters per second. Over here is my velocity. What is my velocity at the beginning? It's 1 meters per second. What is it after 1 second? Well, again, my velocity is constant. So for every second that goes by, I still have 1 meter per second velocity. So a constant velocity on a velocity versus time graph should be a flat line. Okay? So this is what I want you guys to realize. Constant variable, right? Whatever that variable is, if you have a constant of it, on that graph of that variable versus time, it's going to look like a flat line. If I have a constant position, I'm going to have a flat line on my position versus time graph. If I have a constant velocity, I'm going to have a flat line on my velocity versus time graph. What do you think it's going to look like if I have a constant acceleration on my acceleration versus time graph? Should also be a constant flat line, okay? And you're going to see that in the next example. The next thing we're going to talk about is constant acceleration. But we're still on constant velocity, okay? So constant velocity on a position versus time graph is going to look like a slope. A straight line is going to have a slope to it. If you have a positive velocity, you're going to have a positive slope. If you have a negative velocity, you're going to have a negative slope, okay? If you have a velocity on here that's positive, you're going to be on the positive side, right, instead of on the negative side. So if you have a positive 1 meter per second velocity, there you are. And if you have a constant velocity, it's the same for all times, okay? If you're going 50 miles an hour down the highway, it doesn't matter if you look after 1 hour, 2 hours, 3 hours, you're still going 50 miles an hour. What does it look like on an acceleration versus time graph? If I have 1 meter per second squared on here, well, my velocity is not changing with time, is it? I have a constant velocity. So I have no change in my velocity over time. So therefore, my velocity may be 1 meter per second, but my acceleration is 0. It's not changing at all. So again, my acceleration is going to be flatlined along, and it's going to be flatlined at 0, right? Along the axis, the horizontal or the time axis. Okay? Let me redraw this for the next example. Okay, so pretty uninteresting as far as acceleration goes. Fairly interesting as far as position goes. And, okay for, I guess, velocity. Velocity versus time. So constant position, flat line for position versus time graph, doesn't even really register on here. It's just at 0 for both of those. Constant velocity, you get a nice consistent slope here. If you had a negative 1 meter per second velocity, you would have, let's say you start at 3 meters and you're going negative 1 meter per second, you'd have the same type of slope, but it would be opposite direction. If you started at 3 meters and after 1 second you're going less 1 meter, right? You're going in the negative direction at 1 meter per second, minus 1 meter per second, you'd have the same slope but opposite direction, okay? And instead of on here, if instead of having a plus 1 meter per second velocity, you had a minus 1 meter per second velocity, what you'd end up with is, you'd have minus 1 meter per second here, and you'd have a flat line down there for your velocity, okay? So, whatever your slope is of this line, that is your velocity, okay? So, we checked out constant position, we checked out constant velocity. What does constant acceleration look like? Okay, so let's take a look at what constant acceleration looks like. Let me go ahead and fix this up, clean this up a little bit more, so we can keep a hold of all this. Should have an arrow out there. Time keeps on going no matter what, right? I'm going to be less lazy on my graphs. I should be a little bit better about them. Okay, well, let me go ahead and just redo this one because it's starting to look kind of crowded up here. So here is x, going like this, in meters times in seconds. And this is meters per second squared for acceleration, and just flat out meters per second for velocity, okay? So, okay, now let's look at last case of constant acceleration, all right? So, remember that final position formula we had. Initial position plus velocity, initial, however fast we're going to begin with, for however much time, plus 1/2 our acceleration times however much time has gone by, okay? So what does our position look like if, we have 0 for these other values, but we do have an acceleration and it's constant? Okay, so all those other things were 0, so we took them out of the formula because we just didn't need them. They start out at 0. We're starting at 0 meters, and we're starting at 0 seconds, right? And we're starting with a velocity of 0. We're stopped, and we're going to accelerate now. What does that look like? Okay, so final position after 1 second. So after 1 second has passed, what do we get? Okay, our final position is going to be equal to 1/2, and we also have to set an acceleration here, don't we? So let's say an acceleration of 1 meter, good grief, 1 meter per second per second, 1 meter per second squared, okay? Every second that goes by, we're going to increase our velocity by 1 meter per second. So after 1 second, okay, what's our final position going to be? Well, it's going to be 1/2, and then our acceleration is 1/2 meters per second, okay? And then our time is actually going to be 1 second, and we got to square this guy. We square only our time, okay? That's the only thing that gets squared here, all right? So 1 times 1 gets us 1, times 1 gets us 1, okay? Because we're multiplying it by this guy, all right? And then times 1/2 gets us 1/2, okay? So if we start at 0 meters per second, our initial velocity was 0, time was 0, initial position was 0. What do we get after we're accelerating for 1 meter per second? After 1 second, you get to, this is 1 meter, we're over here, okay? So after 1 second, we start at 0, we're going to, after 1 second, 1/2 of a meter, okay? But what's our position, our final position, after 2 seconds? So we still have 1 meter per second squared. We still have the 1/2. But now instead of 1, we get a 2. And we got to square it, right? Because it's t squared, okay? So we get 2 times 2, so we get 4, okay? For our time value here, because it's squared. We still have a 1 for our initial, for acceleration. And we still have that 1/2 value, okay? So our final position is going to be 1/2 times 1, still 1/2 times 4, means 2. Our final position, x final, is actually going to be 2 meters after 2 seconds. Okay? So, after 2 seconds, where are we? Well, now we've really started kicking things into high gear. I'm going to change my scale here a little bit, guys. I'm sorry. Let me just go ahead and do this so I can actually fit some more stuff on here. I'm going to make this 1 meter. This is going to be 2 meters, so we can actually see some more. 3 meters. That's quite evenly spaced. We'll call that 3 meters. Here's 4 meters, and here's 5 meters. Okay, so after 1 second, we were at 1/2 of a meter. We were there. Okay, nothing too crazy. After 2 seconds, though, we're all the way up to 2. So now look at this. Our slope of our line has changed, hasn't it? Okay. What about after 3 seconds? So our final position, we have no starting speed, right? We started out at 0 velocity, 0 position, okay? So again, we only have to look at the 1/2 AT squared business. So 1/2, our acceleration is still 1 meter per second. After 3 seconds, well, remember that time piece gets squared, okay? So after 3 seconds, what we're going to get, we square our time, we get 9, okay? So then we still multiply it by our acceleration, which we decided at 1 at the beginning, right? And we still have that 1/2 factor, okay? So we get 1/2 times 1, so we get 1/2 times 9, so now we get 4.5 meters. So our final position is 4.5 meters after 3 seconds. So after 3 seconds here, we're all the way up to right about here. So look, our slope has changed again. And look at what that's doing. We have a straight line kind of between here because we didn't know exactly what happened. But if you imagine, if you keep on going with this, you're going to get an exponential value. You're going to get a nice curve, right? An increasing an exponential curve. What does that look like for our velocity? Okay, so let's work that out with our velocity formula. Okay, let me erase this for a second. We still have our acceleration as a constant, it was 1, all right? Initial position was 0. Initial velocity was 0 meters per second, but we're going to see what happens to our velocity over time. Okay, so a constant acceleration on a position versus time graph looks like a nice curve, okay? An exponential curve. It's going to get faster and faster. If you're decelerating, it'll do the opposite. If you're decelerating, it's going to look like a curve going down, okay? So this is accelerating faster and faster, more and more distance covered. Slowing down, you'd be going really fast at first, and then you'd be slowing down over time, so that'd be a deceleration. I'll show you that in a moment, okay? But for this 1 meter, positive 1 meter per second acceleration, what does that look like for velocity? Well, remember our final velocity formula was final velocity is equal to initial velocity plus acceleration times time, right? Okay, so our initial velocity was 0. I'm just taking it out of the equation because it's always going to be 0, okay? So my final velocity is going to be my acceleration times my time, okay? So what is my final velocity after 1 second has passed? We know we start at 0. We're not going anywhere. We're at rest. We're in the parked car at the stoplight, right? We're about to hit the accelerator. So we hit the accelerator. After 1 second, where are we? Okay, well, we got 1 meter per second. That's our acceleration. Times our time is 1 second. Okay, so our final velocity here is going to be 1 meter per second. Every second that goes by, you're going to add 1 meter per second to it, okay? So you have 1 meter per second here. There's your velocity after the first second. What does it look like after 2 seconds? Okay, well, acceleration times time. That's linear, isn't it? There's no exponent here. So after 2 seconds, 1 times 2 will get us to 2 meters per second. All right, so here, get even divisions on here. Okay, so after 2 seconds, you're at 2. Okay, what is 3? 3 seconds. After 3 seconds has gone by, what does that look like? Constant acceleration on a velocity versus time graph. After 3 seconds, could be a better 3. In fact, let me just erase it. So after 3 seconds has gone by, 1 times 3 gets you 3 meters per second. No surprise there. So again, after 3 seconds, you're up to 3. And what you notice is you have this nice, consistent, straight line, constant acceleration on a velocity versus time graph looks like a straight line. And this is a positive 1, keep trying to put the 1 over, 1 meter per second squared, okay? That's a constant acceleration. If it was negative, you'd have a negative slope, all right? So positive acceleration on a position versus time graph, x versus t graph, you get a nice exponential, positive exponential growth. On a velocity versus time graph, that same acceleration looks like a straight sloping line, positive slope because it's a positive acceleration. What does it look like on an acceleration versus time graph? Well, the acceleration is not changing. It is a constant acceleration. So it's 1 meter per second squared. Okay, you start out going 1 meter per second squared at 0 time. After 1 second, you're still going that. And you end up with a nice flat line. So what does a constant acceleration look like? On a position versus time graph, a constant acceleration looks like that exponential curve. On a velocity versus time, a constant acceleration looks like a nice sloping line with a consistent slope. On an acceleration versus time graph, a constant acceleration looks flat. Okay? What would it look like if it had negative acceleration? If it was a minus 1 meter per second squared? Okay? Well, I'm not going to bore the, whatever out of you. Okay, I'm going to start. If we start at 5 meters, what would we get? We'd get a graph that looks like this. You'd be going really fast at first and then slowing down as you went. Okay? It would still be exponential growth, but actually it would be exponential decay, I guess, here, right? Because you'd be losing at 1 meter per second acceleration. What would my velocity look like? If I started at 3 meters per second, I already had some speed, I'm going down the street and then I hit the brakes, right? And I'm slowing down. What does that look like? Well, that looks like, again, if I have a consistent minus, there I am doing it again, minus 1 meter per second, 1 meter per second squared acceleration, I get a nice straight line on my velocity time graph, but it's now a negative slope because I'm slowing down. And what does it look like on my acceleration versus time? Well, again, it's consistent. I have a minus 1 meters per second, right? So I've got a nice consistent line, but it's in the negative value. So that's kind of what the graphs look like. Don't let this throw you off. If you see a curve on a position versus time graph, it means you have an acceleration. If you see a slope, any kind of a slope other than a flat line, if you see a slope of 0, you got a constant velocity, right? But if you see any kind of a slope on a velocity versus time graph, it means you have an acceleration. If you see some kind of, well, you always have an acceleration. It just could be that the acceleration is 0, right? But if you have some non-zero value for acceleration, you're going to have a straight flat line either above or below the fold, okay? So that is really it. I've been talking too long. My computer has clocked me out here. So there we go.